Hello, this lesson is an introduction to groups and their elementary properties. First, to motivate us in the definition of the group, let us begin with an algebra problem. Let us say, for example, that we are asked to solve the equation x plus 4 equals 7. This is usually called a linear equation, right? So, let us solve this step by step and take note of the properties that we have used. First, in order to solve for x, we need to isolate x on one side, so the solution will be on the other side. So to do this, we have to get the additive inverse of 4 because our intention was to make it 0. So we add negative 4 on both sides as it is. So I've added negative 4 on the right. Then take note that by using associative property, I was able to move the parenthesis, the grouping symbol for the terms x plus 4 to make it equivalent to x plus the quantity 4 plus negative 4. And of course, the fact that the sum of two integers is an integer, 7 plus negative 4 happen to become 3. Now, because negative 4 is the additive inverse of 4, then the sum of 4 and negative 4 has to be 0. Now, we all know that 0 is the identity element for addition, therefore x plus 0 will be equal to x, and therefore we were able to get the solution x equals 3. So take note that in solving the problem, there are three algebraic properties that matter and became important in attaining the solution. These are the associative property, the existence of the identity element 0, 0 being the identity is essential here, and having said that the system has the identity element, the fact that 4 has an additive inverse help us in solving for the solution. These properties are basically the properties that we need in order to call an algebraic system a group. So let us state the definition. So basically a group is an ordered pair G, comma star, where the first component G is a non-empty set of elements. These are the so-called group elements. And the second symbol star is a mapping or a function from G cross G to G. So if you look at the definition carefully, it meant to say that every ordered pair of elements from G gets mapped or gets assigned to another element of G. It is important that the result or the image should be another element of G. This image to whatever element in G is a comma be assigned, it should be the case that A star B must be another element of G. This mapping is also known as a binary operation. Now, of course, so basically a group is just a set where a binary operation, like for example addition, um, is associated so that we are requiring that the three properties or the three axioms are satisfied. As you can see, these are the three properties, the minimum required properties in order for us to solve a linear equation. The first property is that the operation must be associative. And by associative, we mean this. A times, or let's read it times, or star. A star, the product of B and C, must equal the product or the result when A and B are combined first, then C. In other words, the manner where we group elements, whichever comes first, It doesn't matter because of associative property. And because of associative property, we can leave the expression a star b star c without confusion, because just like in ordinary algebra, when you write a plus b plus c, it doesn't confuse you, right? Because why does this matter? Because by definition, a binary operation can only take two elements of G at a time. So what if there are three elements to combine? So the order of operations will matter. But in this case, because the operation is associative, it doesn't matter. So there we are saving time using grouping symbols by just leaving out a plus b plus c instead of putting parentheses. The second action has to be the fact that the set must have an identity element under star. And in symbols, there must be an element. In group theory, this element is usually denoted by E. And this element E, or the identity element, has the property that any element gets multiplied to it becomes the product is the same element a times e equals a. So if you're going to compare this with the previous situation, the identity element under addition is the element 0, right? Because any integer added to 0 is also the same element. Last but not the least is that we require that every element of the group, for linear equations to be solvable, we require that elements must have an inverse under the given operation. By that, we mean if you take any element of G, there must be some other element from the same set from G, so that when they are combined together, it gives you the identity. In the case where the operation is addition, this inverse is actually the negative, right? For multiplication, in the context of multiplication, this element may be the so-called reciprocal. But take note that in a group, we are requiring that every element must have their inverses. Now, by the word order, or the order of a group, we simply mean the cardinality of the set G. In other words, the number of elements of G dictates the so-called order of a group. If G has two elements, then the group has an order of 2. Let me emphasize here that in the definition of the group, the operation need not be commutative at all. So we do not require the operation to be commutative. But in fact, we do not restrict the operation to be non-commutative. Kumbaga, hindi pinagbabawal. If in case the operation is commutative, what is this? I think there's an error here. If star is commutative, let's see. Let's edit this out. If the operation star is commutative, by that we mean a times b equals b times a for any a and b in G, we will say G is an abelian group. So we use the word abelian as an adjective named after a mathematician whose name is Abel. Okay, so the next slides I will give you the basic examples, and these examples will be the foundations and will be the basic examples that we are going to use in the next few lessons. In fact, many of the groups that we will study will simply come from these basic examples. The first example is this. If the symbol plus denotes the ordinary number addition, the following number sets form abelian groups. First, the set Z of integers. Why? Because first of all, the operation addition, when you add two integers, the result is an integer. That is important, right, in the definition of the binary operation. Second, addition of numbers is associative. Third, the identity element 0 is an integer. Fourth, the negative of an integer is another integer. That's why this pair qualifies to become a group. The second example is the set Q of rational numbers. The rational numbers form a group, an abelian group under addition, because first of all, addition is commutative and associative. The sum of two rational numbers is still rational, and the identity element 0 happened to be rational. And last but not the least, the negative of a rational number is still rational. That's why this set also formed a group. The same thing will happen for the set R of real numbers and from the set C of complex numbers. I have a question. How about the set N, the set of natural numbers? So for our purpose, the set N of counting numbers will start with 1, then 2, 3, and so on. Some authors may consider 0 as a natural number, but for our purpose, we will not include 0. This is just a matter of convention. I have a question here. If dot denotes ordinary multiplication of numbers, is the number set C a group? So, if we're going to check one by one, first of all, we know that number multiplication is associative, right? Second, does C have an identity under times or the multiplication? If you think about it, the element 1 behaves like the identity element because any number multiplied to 1 is the same number. So yes, the last property to satisfy is the G3 action. Thus, every element of C have an inverse under multiplication. Now, if you come to think of it, by inverse under multiplication, we actually mean the reciprocal. We know in algebra that 0 doesn't have a reciprocal, or the reciprocal of 0 does not exist. Therefore, that property is not satisfied. In fact, every element of C, aside from 0, has multiplicative inverse. So again, the set C under multiplication does not form a group because of the fact that the element 0 has no multiplicative inverse. So yung system parang sinira nung element na 0. Muntika na siyang maging group except nandun kasi yung 0. So it did not form a group. You know, the same thing will happen for R, for Q, for Z. It is because the element, just because the 0 doesn't have multiplicative inverses. So you might want to ask, what if, sir, we remove 0 from the set? Does it make the set now a group? So let us denote by C star or C asterisk the set C where 0 is removed, because 0 is problematic. So what will happen if we're going to remove it from the set? Is C star now a group under multiplication? If you do one by one check, you can see that it's already a group because every element will now have their corresponding inverses. By the way, the inverse of an element shall be denoted by a prime if the operation is unclear or not stated. If the operation is addition, we use the negative sign. If the operation is multiplication, we normally use the exponent minus 1 to denote the inverse. So it depends on the situation, but for the generic case, if the element is A, the inverse of A shall be denoted by a prime, or in the generic sense. How about r star under multiplication? Yes, because every element aside from 0 has their reciprocal. How about the set Q without 0? Is that a group under multiplication? Again, yes. How about the set Z without 0? Does that form a group? So let's write here now. This is yes, this is yes, this is yes. How about this? The answer is no. Why not? Because, for example, the element 2 is an integer, no? But the inverse, it too has an inverse. But unfortunately, the inverse of 2 is 1/2, and we know that that is no longer an integer. The inverses to be considered existent must be in the same set. Okay, remember that. Okay, second example. These are the integers modulo n. Again, the symbol 0 does not really mean 0 here. The element 0 here represents all the integers that is divisible by n. By the symbol 1, we don't actually mean 1. We actually mean the set of all integers with remainders 1 when you divide by n, and so on. So in the case when n is 4, z sub n or z sub 4 has 4 elements, 4 equivalence classes. 0 represents those integers which has a remainder 0. 1, 2, 3 represents the integers which has a remainder 1, 2, 3 respectively when you divide by 4. In order for you to recall the operation in z sub 4, I have devised this 4-hour clock now. You can see the 4-hour clock here. So when we say 2 plus 3, what do you mean by 2 plus 3 in z sub 4? By that, we mean you simply put the 2 here, you put the hour hand here to 2, then plus 3, that means plus 3 hours. You're going to count 3 hours after 2, so 1, 2, 3. So the resulting r is 1, so therefore in z sub 4, 2 plus 3 is 1. Now of course, we will not do all the possible additions that we can make in z sub 4 because there's a lot. Now in group theory, if the group is finite or it has finitely many elements, we normally present or define the operation by preparing a table or in this case this is called the addition table, or in the generic sense we call this as the Cayley table, named after Arthur Cayley. Okay, so because we know that 2 plus 3 is 1, what we do is in this row that contains 2 and in this column that contains 3, kung saan sila mag-intersect, doon natin ilalagay yung sum. So dito yun. So 2 plus 3 equals 1. So for example, another example, if we have 1 plus 1 in z sub 4 is 2. So dito natin ilalagay yung 2. For example, 3 plus 1, what is 3 plus 1? That's 4, but 4 modulo 4 is just 0. Remember, we use 0, 1, 2, 3 as representatives. So to complete the table, I've completed the table for you, and this is the complete table for z sub 4. Alright, so what do you want to ask? Well, I've already said that this is a group. Of course, we must check if the addition is associative. But you know, addition of integers modulo n is basically derived from adding integers. So we know that it is in fact associative, right? The next property that we have to verify is the fact that an identity element exists in the set. So in this case, what is the identity element? As you can see here, if you look at this column, you see that this is just a copy of this header column, right? So it meant to say that when 0 is added to everyone, it simply copies, right? Similarly, if you look at this row is the same as this row, so it meant to say that if 0 is added on the left of each element, it gives you the same thing. Therefore, this gives us an idea that 0 is the identity, right? Right? How about for the inverses? For example, I have the element 0. What is the inverse of 0? By definition of an inverse, this is the element which when added to 0 gives you the identity, which is also 0. But as you can see from the picture or from the diagram, 0 plus 0 is 0. So therefore, the inverse of 0 must be 0. How about the inverse of 1? What do you think should we add to 1 in order to get 0 as a result? Sino dito ang i-add natin sa 1 para ang sagot ay 0? By looking at this, you see right away that 0 resulted when we add 3 to 1. Therefore, the inverse of 1 is 3. Do you get what I mean to say? So what will be the inverse of 2? What will be the inverse of 2? What will you add to 2 to get 0? If you look at this row, 0 resulted by adding 2 to 2. Therefore, the inverse of 2 is 2 itself. How about the inverse of 3? Well, what will you add to 3 to get 0? So as you can see, 0 resulted from adding a 1. So the inverse of 3 is 1. So in this group, it is legal to use this notation because the group is additive. I sometimes write minus of 0 to be 0, or the negative of 0 is 0, negative 1 is 3, negative of 2 is 2, the negative of 3 is 1. Now I want you to take note that negative 1 here is not the real number negative 1. The negative sign there is just to indicate that you are taking the inverse of the element. Or instead of reading this as the negative 1 equals 3, because that is quite misleading, we instead read this as the negative of 1 is 3. You think of the minus sign here as an operator. I mean, this is the one, the result is the element which when added to 1 gives you the identity, which in this case is 0. So for all the other values of n, as long as n is greater than 1, this is actually an abelian group. By the way, how did I know that the group is abelian? Well, I know that addition of integers mod n is commutative. One way to verify that an operation is commutative is by looking at the Cayley table. If you look at this table closely, for example, what is 1 plus 2? 1 plus 2 is right here. Where is 2 plus 1? 2, 1. Where is the result? Here. So, nagkataon, equal yung dalawa. In general, if we draw a line along the diagonal of this table and fold it in half, you see that corresponding elements are equal. See? Dapat symmetric yung table along the main diagonal in order to say that the group is abelian. Of course, only when the group is finite, because for the case of infinite groups, we cannot make a table such as this because of the number of elements, right? Let's now move on to the next example. Alright, let us consider the set V, which has 4 elements. Similarly, the 4 elements are symbolized as E, A, B, and C. What are E, A, B, and C? E, A, B, and C are functions from R2 to R2. So, in other words, it takes an ordered pair of real numbers and outputs another pair of real numbers. And for their definitions, E takes every point xy to the same xy. So E doesn't do anything, right? How about A? A takes the point xy to the point minus x comma y. If you look at the xy plane, if you try to draw the xy plane, let's say this is xy, where would minus x comma y be? As you can see, minus x comma y can be found here. So you can think of A as a mirror reflection about the y axis. Parang ito yung axis mo. Lahat ng mga bagay na nandito sa kanan gets reflected to the left because it negates the x coordinate. So for example, I have an image here. Let's say I have a heart-shaped figure like here, like that. Then its image under A will be something like this one, right? So ganyan ang ginagawa ng A. How about B? B is now a reflection about the x-axis because it changes the y coordinate from y to minus y while preserving the x coordinate. How about C? As you can see, both x and y are being negated. You can verify that C is actually a 180-degree rotation about the origin. So this is a reflection, 180-degree rotation, and this is the identity. It doesn't do anything. Now, because our topic is we want V to be a group, what do? We introduce an operation. A natural operation, because these are functions, is composition. So for example, if we take the composition of A and B, what will be the result? What is A circle B? In order to know what A circle B is, we wanted to know what does it do to every point xy in the plane. So to get the image of xy under A circle B, we apply the definition of composition. It becomes A of B of xy. Now, B of xy, according to this definition, is x comma negative y. And then we apply A. So as you can observe, the one on the right gets applied first and then followed by A. Now, what is the image of the point x comma negative y to A? What does A do? It changes the x coordinate. It changes the sign of the x coordinate. So the resulting image would be minus x minus y. But as you can see, the same action is being made by C. Therefore, we can say that A circle B is equal to C. Now, I have pre-made here the complete set of possible multiplications and I do it in advance. I just want you to verify this one by one. What can we say about the table? Is this a table for a group? How do we know? Well, first of all, we should verify that the operation or the set is closed under the operation because this has to be a binary operation, meaning to say if the input elements are E, A, B, and C, dapat ang output elements are either E, A, B, and C. But as you can see in the table, wala naman lumabas na ibang functions. Ang lumabas lang din as results are, or as products are, E, A, B, and C. So, closed. Now, naturally, we know that function composition is associative. Now, what's the identity element? You can pause if you want to think about it. And yes, you are right, the identity element is the function e. This is our question. Now, by the way, does every element have their inverses? For example, because e is the identity, anong multiply natin kay e para maging e? As you can see, that's e. No, by the way, for functions, we use the symbol -1 to indicate the inverse, right? Okay. How about the inverse of 2? What will you multiply to a to get a product of e? As you can see, it has to be a. How about b? Same thing, right? How about c? Yes, c itself. So as you can see in this group, so right now we can call it a group because every element gets their inverses. In this group, you notice that every element are the inverses of themselves, right? Unlike in the previous group, although that is also a group of 4 elements, yung z sub 4, no? Ang inverse ng 1 ay 3, ang inverse ng 3 ay 1. Sa group na ito, iba ang nangyayari. That's why we can say that the group z sub 4 is kind of different from this group because of this property. So well, the answer to this question is yes. My question is this group abelian? Absolutely, because if you fold the table along the main diagonal, you see that corresponding elements are equal, right? By the way, this group has a special name in the subject, and this group table or group is what we call as the Klein-4 group. Of course, there are many ways to define the Klein-4 group, but this is only one of those. Let's consider this now. In this example, I will teach you how to construct a group out of a plain non-empty set. Okay, so let X be any non-empty set. Take any kind of set as long as it's non-empty. Then what I want you to do is I want you to collect the set of all bijections that you can make from X to X. Lahat mga bijections, pag sinabi natin bijections, these are one-to-one and onto functions, and therefore, as in the previous theorem, these are the invertible functions from X to X. Well, we know that if alpha and beta are bijections, then the composition is also a bijection. We also know that composition of functions is associative, right? We also know that the identity map, yung identity map, ito yung parang f of x equals x, right? Or idx of x equals little x. Wala siyang ginagawa sa mga elements ng x. It's simply every x in the set simply stays where it is. We know that the identity map satisfies this property that if you try to compose it with any other bijections, then the result is the other bijection, which is alpha in this case. And we also know that if alpha is a bijection, it's invertible, so its inverse and its inverse is also a bijection. And we know that if we compose alpha with its inverse, you get the identity function. That's why this is a group. Although this is a group, take note that function composition is not necessarily commutative. Therefore, there may be choices for X which will make this set non-commutative, or this group a non-abelian one. I think let's have a particular example. So let's say X has 3 elements, 1, 2, and 3. Okay? What are the possible bijections that we can make out of the set 1 to 3? Of course, the very default one is the identity map. 1 to 1, 2 to 2, 3 to 3. I could even take 1 to 2, 2 to 3, 3 to 1. So imagine like you are rotating. We are performing some rotations because 1 goes to 2, 2 goes to 3, 3 goes to 1. Right? So like imagine that you have there are 3 children hand in hand in a circle, and then they will move 120 degrees about the center. One will go, child 1 will go to child 2, child 2 will go to child 3, 3 to 1. Let's denote that by row 1. I could even do this: 1 to 3, 2 to 1, 3 to 2. So as you can see in these examples, no one is fixed in their places, right? 1 move, 2 move, 3 move. Unlike in ID, everybody is fixed. Now we could sort of do this. We could fix 1, and we can interchange 2 and 3. We could also fix 2, and we could interchange 1 and 3, and we could fix 3 and interchange 1 and 2. Do you think there are other bijections? Are there other bijections that you can make? You can verify that there will be none. So there are only 6 bijections that we can make from the set X2 itself. In fact, in general, if a set X has n elements in it, then the number of bijections that we can make is n factorial. Why n factorial? Because these are the different permutations. No? Some books call these permutations, but later on we'll call them permutations on the set 1, 2, 3. We know that there are n factorial elements. I will explain that later. Now, how to do multiplication? Now, multiplication here is composition. So let us say we wanted to know the product row 1 circle mu1. How do you do this? What we do, remember, if we're performing composition, we first apply whatever is on the left. Now, by the way, the domain has 1, 2, 3 in it, so the first thing that we apply is mu1. What does mu1 do? Mu1 fixes 1 and interchanges 2 and 3, like so. And then we apply row 1. Now, according to this chart, row 1 sends 1 to 2, right? So we will put 2 here. Row 1 sends 2 to 3, so we will put a 3 here because it sends 2 to 3, right? And row 1 sends 3 to 1, that's why we will put here 1. Now where's the composition? The composition is this map. Remember that the composition summarizes the actions of 2 connecting maps. So among the 6, which one is row 1 mu1? Which one takes 1 to 2, 2 to 1, 3 to 3? Yes, you were right. So this is that. 1 to 2, 2 to 1, 3 to 3. So the answer to the product row 1 mu1 is mu3. Right? Of course, we will not do all the possible multiplications, right? But I've made a complete set of table for you. Well, we already know that this is a group, right? So what do you notice about this group? First of all, is this group abelian? I don't think so. For example, if you multiply row 1 mu1, it's mu3, right? But if you multiply mu1 row 1, looking at the table, where's mu1 row 1? Mu1 row 1. So the product is mu2, and mu2 is not the same as mu3. So therefore, this group is not abelian in this case. Okay, so let's move on to the next example. This happened to be an example taken from linear algebra or matrix algebra if you wish. So let M2R denote the set of all 2 by 2 real matrices. So they look like this. Okay, ganito. And let by the symbol GL2R, we mean the 2 by 2 matrices with AD minus BC not equal to 0. What do you mean by that? In linear algebra, you recall that this quantity or this element is what we call as the determinant. So GL2R, the set GL2R consists of 2 by 2 matrices, real matrices, whose determinants are not 0. In linear algebra, we know that these are called the non-singular matrices. Non-singular or invertible because they have inverses. Okay. We have already identified this from a basic course in linear algebra. Well, we know that product of two non-singular matrices is non-singular. I think I will give you an example. Let's say A is 1, negative 1, 0, negative 1. Let's say B is 2, 1, negative 3, 1. Okay? For example, what's the determinant of A? Ano yung AD minus BC ni A? AD minus BC ni A is negative 1. Ang AD minus BC ni B ay 2 minus negative 3. That's 5, right? So as you can see, both of these are not 0, right? So these matrices qualify to be in GL. Now how do we multiply them? How do we multiply these matrices? Now ito yung rows by columns. No? But I have a special method for you in order to calculate the product. A, B, you draw this. Lagay nyo dito si A, 1, negative 1, 0, negative 1. Lagay nyo dito si B, 2, 1, negative 3, 1. So the product will be listed over here. Now what do we do? So the product will be 2 by 2. To get this 1, 1 entry, what we do is we take the first row and the first column. And then combine this by multiplication, and then yung products i-add nyo. So for example, 1 times 2 is 2 plus negative 1 times negative 3 is 3. So 2 plus 3 is 5. Next, we take the first row and the second column. Okay? So 1 times 1 is 1 plus negative 1 times 1 is negative 1. So 1 plus negative 1 is 0. Okay? Now, how about this? So we have to combine this row and this column. So 0 times 2 plus negative 1 times negative 3 is going to be 3. Last but not the least, 0 times 1 plus negative 1 times 1 is negative 1. Okay. So my question is, what is the AD minus BC here? You see, AD minus BC is negative 5. Still not 0. This is what I mean when I said that the product of two non-singular matrices is non-singular. It remains non-singular. Okay? Next, this is a basic fact from linear algebra. We know that matrix multiplication is associative. Now, I will not go into proving that this is true because we only have a limited time in this video. Next, the identity matrix acts like the identity element. What's the identity matrix? It's a matrix 1 0 0 1 diagonal with 1 on the diagonals. It has the property that any matrix 2 by 2 multiplied to it, you get the same matrix as the product. And if the matrix is in GL or non-singular, there is in fact a formula for the inverse. It's given in this picture. I want you to take note of this formula. Now this is why we require that AD minus BC be not 0 in this set. It is because the existence of the inverse will depend on AD minus BC being 0 or not. Because if AD minus BC is 0, there is a problem with this formula. Ang isabihin na itong constant na ito na nasa labas, you just multiply it back in to every entry. Okay? So, GL2R is a group. But I want to emphasize that in linear algebra, you know that matrix multiplication is not commutative. There are examples, in fact, in your lecture notes, you can see examples where AB is not the same as BA. So again, GL2R is a non-abelian example of a group. Okay? We next move on to the basic properties of groups. By the way, GL2R, that's why it's called GL, it stands for the general linear group of index 2. In all honesty, we can extend the concept to an arbitrary n by n matrix. There's also the notion of determinants for an n by n case, but for most of our examples, we'll be dealing with 2 by 2 anyway. So first property that I would like to talk about is the identity element. Axiom G2 states that a group must have an identity element, but it did not tell us how many, right? Well, in this theorem, we can prove, because we can actually prove that there can only be one identity element in the group. To see why, so let's assign an operation star on G, okay, to prove the uniqueness. The existence is already guaranteed by G2, so we only have to prove uniqueness. To prove uniqueness, we usually suppose that there are two such elements, let's say E1 and E2. Now, because these are identity elements, by definition of identity elements, for E1, let's say, if you multiply any A on the left of E1, then it must be the case that the product must be A, and that must hold for all A in G, right? Similarly, because E2 is also an identity element, any element multiplied on the right of E2 must give you the same element as the product. In particular, take note that E1 and E2 are also elements of G, right? So if we are going to use this, equations, so for example, if I use equation 1, I know that E2 is E2 times E1 because I'm going to replace A by E2. E2 is one among those elements in G that satisfies equation 1. So if I replaced A by E2, you will get this equation. Now looking at this expression, I can make equation 2 as a reference. You see that E2 is on the left, and I can treat E1 as an element of G, and according to the equation 2, E2 times E1 must be equal to E1. Therefore, that finishes the proof. Why? Because if you suppose that there are two identity elements, you can, well, prove that they are just the same. So, no two identity elements can exist in a group. There could only be one. And because there is one, by G2, there is a unique identity element. Now, usually identity elements in a group or in generic, we symbolize that by a symbol E, no? Usually authors use E as a generic symbol for the identity. Some others use, when they're using the multiplicative notation, some others use 1, some others use 0 if the operation is additive. But this doesn't mean that they are really the elements 1 and 0 as they are numbers. No. Another property is the fact that every element in a group has an inverse. But the axiom G3 did not tell us how many inverses can there be for an element of a group. In fact, the next result tells us that an element in a group cannot have more than 2 inverses. Why? Let's prove. So, suppose A is an element of a group G with identity E. And again, to prove the uniqueness, we suppose that there are 2 inverses for A. So suppose that A prime and A double prime are inverses of A. What do you mean by inverses? It meant to say that if these elements get multiplied to A, we get the identity. Hence, we have the following. Right? Also, we have this, because these are inverses of A. Now, these equations, together with axioms G1 and G2, will give us the following. Look at A double prime. Because E is the identity, A double prime times E is A double prime. Now, by equation 3, I could replace this E by A star A prime. And by G1, which is associative property, I can move the parenthesis there. And by equation 4, this is equal to E. And by axiom G2, E times A prime must be equal to A prime. And that proves that the inverses A double prime and A prime are just the same. So uniqueness is now guaranteed. So in our case, if the operation in the group is not specified, the inverse of A will be denoted by A prime. But for example, if we're working on the group of integers, for example, the operation there is addition, so the inverse will be denoted, we will stick with the convention minus A. If we're doing it in the set of non-zero real numbers under multiplication, the inverse will still be A to the minus 1. So it depends on the situation. But for the generic case, we should be adopting the prime notation, unless otherwise stated. These are some corollaries to that. Syempre, if A prime is the inverse of A, it must follow that A is the inverse of A prime. Right? So that's why property number 1 is kind of trivial. The second property is what I call, or what most of the authors call, as the shoes and socks property. It is because when you try to wear your shoes and socks, of course you do it socks first and then your shoes. In order to undo that, you have to remove the shoes first before the socks, right? Hence the shoes and socks property. If you want to undo the combination of the two actions, you have to do the last action done first, then the first one. Okay? In fact, this even extends kahit na ilang elements meron ka. Let's say you have something like this, and then kung may inverse, mangyayari an inverse an minus 1 pabalik. Kasi kung ano yung huli mong ginawa, yun yung una mong i-undo to undo everything. Tatanungin nyo ko, Sir, bakit sa algebra ang ab to the minus 1 is a to the minus 1, b to the minus 1? Yes, kasi yung algebra nyo noon ay abelian. Commutative ang multiplication nyo kasi noon. But in general, if multiplication is not necessarily commutative, just like in the case of groups, you do not assume this. Okay? So to prove, well, hindi ko na ipoprove yung 1 because that's kind of trivial. Let's try to justify 2. If you're going to read this, it says that the inverse of A times B is the inverse of B times the inverse of A. So it amounts to proving that this is the inverse of A times B. So what I do is I multiply them together. If you multiply them together using associative property, we get this. B times the inverse of B is the identity. And then of course that's the identity, so you can remove it, you can drop it, it could be A times the inverse of A, and finally that's the identity. Similarly, if you do it the other way around, magka-cancel tong dalawa, mawala yan, magka-cancel to, and finally E. So it only means to say that the product of these two is the identity regardless of the order, therefore they are inverses of each other. This is why we can say that the inverse of A times B is the inverse of A times the inverse of B. Sorry, the inverse of B times the inverse of A. Okay? The third property that I wanted to tell you is very important because this is being used a lot or a number of times. This will be used a number of times in the semester, and this is what we call the group cancellation law. It says that if you are in a group, okay, and you know that A times B is equal to A times C, just like so. And because A is common on the left, right, you can cancel. And then you can conclude that B is equal to C. Now we call this the left cancellation law because the one being cancelled is on the left hand side. Remember that in a group, the operation need not be commutative, so be careful. We have to distinguish left from the right. So, how about the right cancellation law? The right cancellation law, nasa kanan yung kinakancel. Basta may parehas na bagay sa parehas kaliwa or parehas kanan, you can cancel. Gusto mo isama mo na i-cancel yung kaklase mo. Joke lang. So, just like this, AC equals BC will also imply that A is equal to B. By the way, word of warning, kapag ang common na factor, let's say A times B equals C times A, in this case, you cannot just cancel A because they are on different sides of the equation. No. Different sides or different orientation. Nasa left yung A sa kaliwa, nasa kanan yung A na nasa kanan. So you cannot apply the cancellation law. You should be careful. Because C times A may not be equal to A times C. So in order to prove, ang gagawin ko lang yung left cancellation law, and then I would like you to do the second one as an exercise. So we will assume that A times B is equal to A times C. We wanted to prove that B is equal to C. How? Well, we start with B. Take note that B is E times B. Then, this E, I would like to replace this E by A prime times A because, well, the inverse of A times A is E. Then I will use associative property. Okay? So, mag-group yung A times B ngayon. But by hypothesis, A times B is A times C. So I could replace A times B with A times C, just like so. Okay? Then finally, I could apply again associative property and move the parentheses over here. So A inverse times A is E, the identity. Finally, E times C is just C. So as a conclusion, B is equal to C. That proves the left cancellation law. Okay? And we now move on. By the way, before we move into the final property, this is, well, another version of the group cancellation laws. If you take the contrapositive of the statements there, it says that if B is not C, then AB, kapag multiply ka man ng dalawang parehas na elements both on the left, yung product na yun ay hindi parehas. Contrapositive lang ito ng LCL. Ito naman pangalawa ay contrapositive ng RCL. That's why they are equivalent. I think there's an error here, sorry. this should be star. Okay. Now, I also call this as the Sudoku property, or this contrapositive. I usually call this the Sudoku property. Why? Because, diba, in the Sudoku table, no elements on any row or in any column can be repeated, or they cannot be repeated. It is because if you have a group table, if you're working with a finite group and the group table is available, you notice that no elements are repeated in every row and in every column, just like in our examples. You can rewind now and see for yourself. And these properties guarantee that. Why? Let's see. If we try to draw a Cayley table, let's say I have two elements B and C. They are not the same. Okay? And I have here an A. Remember that I am going to write the product A times B over here. Then the product A times C over here. According to the first property, A times B must not equal A times C. So, mean to say, in a row containing A, if you're in two different columns, the elements that you see are not the same. Therefore, in any row, no element is being repeated. The second property now talks about the columns, and you just have to work your way to find out why. Okay? The last property is actually where we started. We talk about linear equations, right? Well, this simply confirms that in a group, or the group properties are the minimal and the properties that we need in order to solve linear equations. So you see the vibes why this subject is called abstract algebra, right? Because we're solving equations. What does it say? So we are in a group again. There are two elements A and B in the group. So we have the equation A star x equals B. And according to the theorem, this equation has a unique solution for x. Similarly, if the unknown variable is y and it's found on the left, just like here, we have to distinguish these two cases because, again, a group need not be commutative. This also has a unique solution for y. So take note that I'm going to prove only the first part. The second part is parallel, and I want you to do this as an exercise. Okay, for 1. Now note that the claim proves that there is a unique solution. Pag ganito yung theorem has a unique solution, there are two things to prove. First, that it has a solution. Second, that the solution is unique, or existence tsaka uniqueness. For the proof of existence, you just need to prove that a solution exists. Magbigay ka lang kahit isang example. For the uniqueness, you know what to do. Standard protocol. Suppose that there are two and prove that they're actually the same. Okay, so let's proceed. For the existence, take note that since A and B are in G, yung inverse ni A ay nasa G rin. Because B is in G, the product A inverse times B is in G. Right? So, itong element na to, siya yung kandidato natin. Tatawagin ko siyang X. And we will check that this is indeed a solution. If you plug it in on X, so this is what will happen. Ito na yan, nilagay ko na siya sa X. Using associative property, I can move the parenthesis over there. A times A inverse is the identity times B. Identity times B is B. Therefore, you see AX is equal to B, and therefore this X satisfies the equation. So therefore, we have proven that this equation has a solution. For the uniqueness, on the other hand, right? So suppose that x1 and x2 are both solutions to equation AX equals B. So it meant to say that both x1 and x2 satisfies this like so, right? Because both the right hand sides are b, it meant to say that the left hand sides are actually equal. And this being equal, you notice that a on the left of each side is a common factor. Therefore, by the left cancellation law, you can cancel a and conclude that x1 is equal to x2. And that completes the proof. And this also concludes the lesson. So you see that the group properties are basically the minimal properties that we need in order to solve a linear equation. In the next lesson, we are going to talk about subgroups. These are groups that are found within a larger group. Okay, see you in the next video.